So this one's a little more challenging. What they're doing here is they're saying, okay, here are the products, and they want to know what are the two starting materials. H plus is involved. So notice, one of the things to remember about all these reactions, these imines, these hemiacetals, check out that arrow. Right? That's an equilibrium arrow, meaning the reaction goes both forward and the reverse direction, right? And of course, we can talk about how we shift equilibrium, right? We could remove one side, right? We talked all about those things, about gases, about drying agents even maybe. You could distill things out. Either way, shifting equilibrium. We hopefully kind of have an idea on that. But here, or adding a lot of one reagent to push it to one direction, right? You can do those kind of things. The question is, what was this before? Right? So it's kind of throwing you for a loop maybe because there's a sulfur there. But this should look pretty similar to something we're going to start talking a little bit more about. These acetals. This is an acetal. We just started talking about it. This is a thioacetal, meaning it's the sulfur. What could these come from? So this is actually a way to do protecting groups. It's kind of like, I always like to think of it, it's like a mask. You're putting a mask on this functional group to kind of make it less reactive. And of course, what kind of functional groups have we been talking about this whole chapter, this whole unit? Ketones and aldehydes. So if you looked at this, right, this carbon right here is kind of where the action's at. You see it's bonded to two sulfurs. If you take one step back, hopefully it's not a huge leap to realize, well, this was a ketone, right? There was a ketone there. And the other piece, if I'm thinking about breaking this, would be this sulfur and the H's. Now notice what I did. Just some good way to think about stuff. I have an oxygen. I have an oxygen. Right? Hydrogen. 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 Right? Where were things in the starting material, or where were things in the products in this case, going backwards to the starting material? Now, mechanism-wise, we'll talk more about this later, but kind of at this point, I want you to be able to see these things. You could think, right, what's the first step, right? If I just kind of flip this around, what might the mechanism be? So let's just, for ease of looking at it, right? You have H plus now. Now we're going the, right, I've essentially just turned this around, right? Because it doesn't really matter, equilibrium arrows. What's the first step going to be? You have H plus. What's the first step going to be? Protonation, right? You're not going to protonate the water. What you're actually going to do is protonate the sulfur. So you protonated the sulfur. Now the sulfur has a plus charge. And it's kind of like the reverse of what you had before when you were adding an acetal. You have a tetrahedral intermediate. Do you have a good leaving group? All of a sudden this is a good leaving group, right? That's been protonated. The sulfur's electrons here can come down. That opens that up. Got to balance my charge. Where should there be a plus charge? On the sulfur. Don't forget, our friendly water is floating around. All right. So now water reacts. Goes in there. Adds in. We'll make another tetrahedral intermediate. All right, oxygen has a plus charge now. Now we know at the end of the day, right? So you started recognizing these things. Hopefully, you want to get the sulfur carbon bond. You need to break those bonds, right? So what do we need to do here now? We need to make this a better leaving group, right? Because right now the best leaving group is water on this tetrahedral intermediate. So we need to make this a better leaving group, and the way that we do that is proton transfer. All right. So I wrote PT for proton transfer. The hydrogen from this oxygen transfer over to this sulfur. Don't need to show arrows if you don't want to. Now this is a better leaving group. And of course, it wasn't mentioned, but I would always mention it. This H plus is a catalyst. So if I want to be doing it in one fell swoop, or I could take 2 steps, I could. If I break this OH bond and those electrons come down, I make that new pi bond, and I kick that sulfur out. I do that elimination. And what do I end up with? I end up with this, the H plus. Right, this H plus is this. And I also end up with the thiol group here as well. So these mechanisms, right, you should be able to know them forwards, literally forwards and backwards. Right? They have a lot of the same intermediates. It just matters where do you want to put the proton to make something else a better leaving group. What are you trying to push on or push off? So for this one, you have 3 things in the mixture. And of course, our H plus is a catalyst. But the difficulty for this one is they actually don't allow you to grab the H plus. Because the first step in acidic conditions is what? Protonation. And you'd be protonating, in this case, the ketone. But the way this is set up, it won't let you do that. So this won't let you actually use the H plus catalyst. So that's kind of silly and a hindrance of trying to answer this. So the only thing you can do is just have the nucleophile, the amine, react with the carbon in the carbonyl group. And then they ask you, they literally says, several steps. Well, yeah. And you're missing the first step. Right? Because, of course, the first step should be what? Protonation. But we're not able to do that, so he's got to go on to this. And the thing you make with a primary amine and a ketone, in acidic conditions, you make an imine. So you should be able to draw that right away. I always just draw the ketone like it's there, and then put a nitrogen. And, of course, you also made water, but they're not asking you for they're only asking for the organic product. Notice water doesn't have carbon, so it's not an organic product. So that's all they want in that case for that step. They take it a step further. Okay, so then very similar to things we've done in a workshop, they have a ketone again, but now instead of a primary amine, right, a nitrogen is bonded to 1 carbon, they have a secondary amine with a ketone. So what does that form? If there are hydrogens, right, these alpha hydrogens, we call them alpha hydrogens, hydrogens that are 1 bond away, or alpha carbons that are 1 bond away from the ketone. If these carbons have alpha hydrogens, right, these alpha hydrogens, a ketone with a secondary amine in acidic conditions gives you an enamine. An enamine. This is an imine, and now I'm going to draw an enamine. All right, this is an enamine. So what happened, let's say this hydrogen was pulled off, right? And now there's only 1 hydrogen left on this carbon because there were alpha carbons with alpha CHs, right? Alpha meaning 1 bond away from the carbonyl. That got us to an enamine. But again, I would argue the first step should be what? Protonation, right? So what they want here is you to do this first step, which of course I would argue is the second step. And then they say several steps. They just want you to get practice about what's the nucleophile, what's the electrophile. But really the first step is protonation. Always in acidic conditions. Use the proton first. Okay. Ranking question. The question is asking us here to rank these from least electrophilic to most electrophilic. So the first part you need to realize is what exactly are they talking about. So these are all either aldehydes or ketones. And what they're asking about is really the carbon of the carbonyl group, the acetyl bond O for each of them. So whenever I get ranking problems, I try to think of get the limits, the highest and the lowest. between these. So if we're talking about electrophilicity, I would be looking for things that are delta plus. And if something has a full plus charge, that should be a dead giveaway that that's probably the most reactive. And that's what this is. So this would be the highest. So I would rank this one as the most electrophilic. All right. Now, one thing we did talk a little bit about was the difference between the reactivity between an aldehyde versus a ketone. We talked about two things. We talked about an aldehyde. The easiest thing maybe to see is an aldehyde is less sterically encumbered because there's an H here versus a carbon and 3 hydrogens. So it's easier to get to aldehydes, so they're more reactive because of sterics. A nucleophile can get there easier versus a ketone, which would have, right, much more bonds, 6 bonds, 2 bonds away, making it less sterically accessible. Also, ketones can have hyperconjugation where sigma bonds, right, 1, 2 bonds away. So these hydrogens can also help donate electron density towards this carbon, making it less electrophilic. So aldehydes are more reactive than ketones. Things with a plus charge kind of override all of that. So this would be number 1. Now, knowing what we know about here that aldehydes are more reactive, so then we look at the 2 aldehyde options. Okay? So the 2 aldehyde options, and what's the difference between these? Well, this aldehyde, both have H's. This has a CH3, 3 H's, and this has a CF3. Well, what do you know about fluorine? Right, where's fluorine at in the periodic table? Fluorine is very electronegative, so it's very electron withdrawing. Right? It's going to pull away electron density. That's going to make this carbon that much more reactive, right? It's going to make it more delta plus. So I would say this would be number 2. Aldehyde is probably number 3, right? Because it's head of ketones. And now I have these 2 ketones. Well, what's the difference between these 2 ketones? This ketone has this tert-butyl, a much bulkier group, right? This has CH3, CH3. This one has a CH3. This one has a C, CH3, CH3, CH3. Right? This is going to be a much more bulkier, sterically encumbered position. So I would say this would be 5, and this would be 4 for that ranking. All right, we have an aldehyde, and we have sodium borodeuterohydride. We have this D. What does that tell us? That tells us we have heavy hydrogen, which is hydrogen with an extra neutron, but it's still like a hydride source. So what this really is, right, of course, is boron with all these D's, the negative charge, but really, at the end of the day, it's just this. So it acts the same as H minus, it just has an extra neutron. So it's just a little heavier. Cool. Mechanism-wise, first step, you should recognize we're in basic conditions because we have hydrides. So the first step is going to be nucleophilic addition, add into the carbonyl. So we do that addition. We, of course, make a tetrahedral intermediate. We just added a D. Anytime we have a tetrahedral intermediate, we ask ourselves, do I have a good leaving group? Do you have any good leaving groups? Nope. So now you're going to do protonation. So you're done with your step 1. Now step 2 is going to be protonation. So H3O plus is the same as H plus in water. All right, you can just draw it as H plus. What's going to happen? We're going to get protonated. And that's going to leave us to a final product. H and D. So that gets us to our final product. I think another version is you could have deuterated water. So you could add, so instead of having H3O plus, you have D3O plus. So there'd be a D here, and then you'd add the deuterium to the oxygen instead. So just keep track of those things for the mechanism.